Hello, this is Jack Ingram, and this is Lab 3, Black Hole. Introduction. In this lab, we are observing a star orbiting a black hole. We will be observing the motion of the star in order to find its net force. The only force acting on this star is from the black hole. We will be using GlowScript to build a model to predict the motion of the star. We will use Newton's second law, the momentum principle, and Newton's universal law of gravitation. Fundamental principles. Newton's second law states that the acceleration of an object is equal to the net force divided by the object's mass. Newton's universal law of gravitation states that a particle attracts another particle with a force given by the following equation. The force of gravity is equal to the universal constant g times mass 1 times mass 2 all over r squared. We will also be using parallel and perpendicular momentum. The first thing we did to start building our model was set the initial conditions. Here we set g equal to 6.7 times 10 to the negative 11, the mass of the star to be 2 times 10 to the 30, delta t to be 86,400, and our t to start at 0. The next thing we did to build our model is the calculations. First, we made initial and final momentum vectors p underscore init and p underscore final. Then we made delta v equal to v final minus v initial and delta p equal to p final minus p initial. Next, we created the change in momentum with respect to time by dividing delta p by delta t. And here we use Newton's second law. Since net force is equal to the change in momentum, we are just able to set these equal to each other. Next, we'll calculate the parallel change in momentum with respect to time. And again, we will use Newton's second law to set the F-net parallel equal to the change in momentum with respect to time parallel. Then we will do the same thing with the perpendicular. Finally, we will use Newton's universal law of gravitation, moving around to solve for the mass. The final adjustment to the starter code was setting the position and axis for the 3 arrows in our code's output. As you can see here, arrow 1 represents the net force, arrow 2 represents the perpendicular net force, and arrow 3 represents the parallel net force. Here's what it looks like when we run our code. As you can see, our net force is 8.42184 times 10 to the 28. Our parallel net force is 2.37785 times 10 to the 28. And our perpendicular net force is 8.09118 times 10 to the 28. What does it mean? Discuss the differences between net force and its components and change in momentum and its components. Well, we know that the net force and its components are equal to the change in momentum and its components according to the momentum principle. Net force is found using Newton's universal law of gravitation, since the gravitational force is the only force acting on the system. And though these values are the same, they are calculated in different ways, so the change in momentum is found by using the change in velocity as we did in our code. What if? Imagine the black hole whose mass you found was removed and a different black hole was placed in the same location. Assume the motion of the observed star remains unchanged and is affected only by the gravitational force of the new black hole. Could you tell the difference? No. Since the star would have the same trajectory, we would still have the same output and thus the same mass, so the mass would not be any different, and we could not differentiate this black hole from the other black hole.